made, but we're going to be talking and going over Mechanum wheel drivetrains and field-centric drive. Let me share my screen. Okay, here's their demo in the virtual robot thing. So we have omnidirectional lateral control on one joystick, and I think here the triggers give you rotation, and then, oh, this isn't exactly field-centric, but in a field-centric system, we'd expect if you raise the joystick up, the robot would go this way, not just straight forward. What it's doing right now is how our robot setup is robot-centric drivetrain. So I made a little presentation about field-centric drivetrain I can show, I guess. All right, so the goal is no matter where the robot's facing, it'll move in the direction that the joystick is pointing. So if you're facing this way and you point the joystick up, you want the robot just to move up, which is an angle of 0 degrees. So our first step is to get our joystick angle. This is going to require like a ton of trigonometry. I'm going to share this presentation at the end so you can like check the math and stuff and use that. Um, I guess I won't share I don't know, I might share the code later on, but we don't really use field centric that much, so I'm gonna have to make my own code and test it. I just thought that this virtual robot thing might have that. But first get the joystick angle, and you do that by taking the inverse tangent. So that's your y component over the x component, sine over cosine. And that's how you get this angle between the horizontal and where our joystick is at. And then our next step is to get the robot angle, which you're going to use the IMU to do, just like how I taught last week. And this is the z-axis angle, depending on how you set up your robot or your control hub orientation. Now, the hardest part of this entire process is normalizing the joystick angles. So, and the robot angles. So our joystick angles go from 0 to 90 to 180 to 270 down here. But we want it to be like this, 0, 0, 90, 180, 270. So what we're going to do first is everything from 0 to 270 degrees, we're going to multiply the angle by -1 and add 90 degrees. And everything from 270 to 0, we are going to multiply the angle by -1 and add 450 degrees. And that gets it on this scale. So I have pseudocode in the presentation as well, which I'll share. Okay. Now, the next step is to normalize both the robot and joystick angle. So this scale right here that we just changed our joystick angle to is going to be exactly what the IMU is seeing. So 0, 90, 180, -90. We talked about that last week. So both the robot and joystick angles are on the scale, and we want to switch it from 0, 90, 180 to 70 because the negative numbers on this side make it kind of hard to work with. So in pseudocode, if it was less than 0, we'd add 360, but if it was greater than 0, then we do nothing. All right, now we want to find the lateral travel angle. So Mechanum wheels work by, I'll go back to that slide, but Mechanum wheels work by providing a force at 45 degrees diagonal. So, and this combination of wheel speeds that you use on your, that that you give to the wheels, they like add to each other and will allow your robot to travel at multiple different angles, not just 45 or straight. So you can travel basically wherever the joystick is pointing. I'll go back to that. All right. So what we're going to do is we need to make sure that this lateral triangle travel angle is always positive. But if not, it'll affect the motor output. And like if that's negative, then that'll kind of like ruin our algorithm. So if a robot heading is greater than the joystick angle, then we take 360 minus the robot heading and add it to the joystick angle. But if it's less than that, then it's just joystick angle minus robot heading. I think there's a better way to do this. You might want to go to game manual 0 Mechanum wheels. Yeah, it has field centric code here. It has the yeah. Um, it it's doing it in a simpler way, but what the way I'm explaining is like how the math works and stuff, and it's the same end result. So yeah, that's for the lateral travel angle and our travel equations. Okay, so yeah, the Mechanum wheels provide a force at a diagonal. This means that when the lateral travel angle is a multiple of pi over 4 radians, which is 45 degrees, then one set of diagonal wheels should have an output of 1, and the other should have an output of 0. So if you plot that, then we get our front left at 45 degrees. Front left and back right should be at power of 1, and front left right and back left should be 0. And I keep doing these for all the multiples of 45. And then we can plot these, and we find the travel equations by finding the trigonometric functions that run through these points, which is sine of x plus pi over 4 and cosine of x plus pi over 4. So for your back left and front right wheels, it's sine of lateral travel angle plus pi over 4 times your magnitude, which is, let me go back here. Magnitude is going to be this value over here, which using Pythagorean theorem, we find is y squared plus x squared, all of that square rooted. And then for back right and front left, we take the cosine of the lateral travel angle and add pi over 4 and multiply it by magnitude. Or the same thing is sine of lateral travel angle minus pi over 4. They're essentially the same function. So yeah, and then to add rotation, we just subtract rotation from the left side wheels and add it to the right side wheels. If you want to, you can do some scaling in there, which will um, make sure the powers go from 0 to 1, because sometimes when you add rotation and your power is already like 0.7, then the motor power will try and go to like mathematically it won't work, is what I'm saying. But you don't really need to do that. Just subtract the rotation from the left side and add it to the right side, and you can have rotation with field-centric drivetrain. What is this missing? Okay, it's just missing the IMU completely. Okay, all right. So ours is the same. It's just a robot-centric holonomic omnidirectional drivetrain, and I'll walk you through some of the code here. And this line that we commented out is what turns it from robot-centric to field-centric. So here's a function robot-centric plus. I will put this function on the GitHub. So we need double X, Y, magnitude, radians, and wrangle, which is robot angle. We're going to get X from the gamepad1.left stick X and Y from gamepad1.left stick Y. So field-centric multiplier is a way we can reverse our motors. So if we press like a button on gamepad 1, then we can just reverse the drivetrain if it started off in inverse. Or if we want to, we can also make it slower as well by turning down making field-centric multiplier less than 1. And our rotational double here that we're adding to the right side and subtracting from the left side, I think, is going to be gamepad1.right stick X, or you can use right stick Y, or you can use the triggers, but I like to use right stick X. And then we're multiplying it by rotational mult because we can slow down our spinning speed there. So we find the magnitude by squaring X, squaring Y, adding them, square rooting both of those. And then we find the angle of the vector for our joystick, arctan, which is atan2. And then, what does this do? Okay, so this normalizes it. So if radians are greater than or equal to 0 and radians are less than 270, then -1 times radians, we negative that and add 90. Or if not, then we negative it and add 450. To get the robot angle, we just get the IMU.get angular orientation, and this one is going to be our Z angle. And then to put them on the same scale, it's just going to be the same code for both of them, which is finding if the radians are less than 0, or the angle is less than 0, and then adding 360 to it. And if not, then we do nothing. Last reset position here is a way you can ignore these 4 lines because what they do is they allow you to click a button on the gamepad. I think the code's somewhere up in the top of the file. But you click a button on the gamepad, I think, and it resets your robot angle relative to the field. But that wasn't used very much, or at all, I don't think, when we use field-centric. Okay, now turn is, I apologize for the bad variable names, but turn, we're just going to set equal to our robot angle here for robot centric. But if we want to do field centric, then we're going to use this right here, the lateral travel angle formula. So if the joystick angle is less than robot angle, then we 360 minus robot angle plus 0 minus, what is that? Joystick angle, sorry. I'm tired. But if not, then we just take our joystick angle and subtract our robot angle. And that's the value we plug into here. And then if you're using that, then you just comment out this line. So I'm going to go ahead and put this on the GitHub. But yeah, that's all I had for this week. I'll send out the recording, and this is the last week, so no more classes, but I also have some YouTube videos that we made and we were going to edit out on color sensors and also computer vision with OpenCV, which might not be that helpful because computer vision with OpenCV is kind of being phased out, I feel like, especially since there's no randomization this year. But the normalized color sensor stuff is a hidden gem I found, I think. All right. Thank you guys so much for coming. And I really hope you guys learned from this experience.